All right, buckle up because we're doing the whole study guide right now. All right, start at the very top here. So we're going to go through naming first. So we have magnesium and then we have PO4. So anytime we're doing naming, okay, if it's not an acid, we start with the cations. This is magnesium. Okay, and then PO4, we're going to go to our magic table of polyatomics. Okay, so PO4. PO4, where is that? Ah, it's right here, phosphate. Okay, so it's going to be magnesium and then phosphate. Okay, so when we're working with polyatomics, so things that come off that table, we do not change the ending. We just leave it exactly like it is. All right, next we've got SNO. So SN is tin. And if you go to your periodic table, so let's scroll back up here. So on the periodic table, tin is in group 4A. Tin is one of those that has a variable charge, so we have to look at what it's attached to. Okay, so oxygen has a charge of -2. Remember, all ionic compounds are neutral, so that means that tin, in order to balance this out, has to have a charge of +2. So we don't just write tin oxide, we need to indicate what the charge of tin is. So we're going to use Roman numerals, so this will be tin 2 oxide. All right, next we have copper and bromine. So copper, Cu, is on our periodic table. So it's in the middle section right here. So in that D block, remember, we have transition metals and they have variable charges. We have to look at what it's attached to. Okay, so bromine right here, bromine has a charge of -1, but there are 2 of them. So that means we're going to have a total negative charge of -2. So let me just change this. So because there's 2 of them, it'll be -2. Okay, and then to balance this out, copper has to be +2. So just like we did up above with tin, this is going to be copper 2. And instead of bromine, we're going to change the ending, so it's going to be bromide. Okay, so just like with oxygen, we're going to end in IDE. If it's not a polyatomic, so if it's just oxygen, if it's just bromine, we change the ending to IDE. Oh boy, number 4 looks like a mess. So let's look at what we've got here. So NH4 is one of those weird things from the table here. So we only have 2 of these. If you go and look on your table, in the lower right-hand corner here, we have polyatomic cations. Okay, so NH4 is ammonium. So let's write that out. So we have ammonium. Okay, and then NO2, again, let's go to our table and let's find it. So NO2 is nitrite. That's it. We don't have to change any endings. Since these are both polyatomics, we just leave them alone. We just write them out like they are. Okay, so for the next one here, we have CS, which is cesium. Okay, so this first part, the cation, we always just write it out. Okay, and then we have phosphorus. Phosphorus is by itself, so instead of it being phosphorus, we're going to change the ending to IDE, so it's going to be phosphide. Okay, and again, there's our ending, IDE. All right, for this next one, HNO3, since it starts with H, we know it's an acid. Okay. The other thing we're going to look for if it's an acid is we're going to see if it has oxygen, which it does. So because it has oxygen, we're not going to see the prefix hydro. Okay, NO3 on our table here. So NO3 is nitrate. Since it ends in ATE, we're going to change the ending. So it's going to be nitric. So RIC, so we change the ending to IC, nitric acid. And again, we don't have hydro because this has an oxygen. Okay, HBr, again, we're starting with hydrogen, so we know it's an acid. I do not see an oxygen here, so this is going to be hydro. Okay, and it's bromine, but we're going to change the ending to IC, so it's going to be hydrobromic acid. Okay, next we have, again, starting with hydrogen, so it's going to be an acid. The next thing we look for is an oxygen, and oh, look, there's one right here. So no hydro this time. SO3, we go to our table. SO3 is right here. It's sulfite. Okay. Now, sulfur, remember, is tricky. So instead of just changing the ending, we're going to go back to sulfur. Okay. Now, because SO3 is sulfite, it ends in ITE, we're going to change the ending. Instead of it being IC, it's going to be OUS, sulfurous acid. Okay, moving on, we have PB, which is lead. And if you recall, lead is in that transition metal area of the periodic table. So lead, PB, oh, sorry, it's not a transition metal. It's in group 4, but lead is one of those that has a variable charge. So lead, we have to look at what it's attached to. So it's attached to sulfur, and there are 2 of them. Sulfur is right here. It's in group 6A. So remember, everything in 6A has a charge of -2. They need 2 more valence electrons to get to 8. So if there's 2 of them, 2 times -2 means we have a total negative charge of -4. So lead has to be +4. So this is going to be lead 4, and the Roman numeral for 4 is IV. And then sulfur is S. We're going to change the ending to IDE, so it's going to be sulf, and then IDE, sulfide. Right, next we have aluminum and nitrogen. Just like all the other ones, except for our acids, of course. The cation, we just write it out, so it's going to be aluminum. Okay, and nitrogen, we're going to change the ending of nitrogen to IDE. Nitrogen is just nitride. And that's it. So those are all the namings. Let's go down to the next one here, and we're going to write out the formulas. So let's start with barium and chloride. So chloride is chlorine. So barium, Ba, has a charge of +2. Chlorine, Cl, has a charge of -1. So to make this work, since barium is a +2, we need 2 chlorines. So this is going to be Ba, Cl, and then again, we need 2 of those to make it work. All right, ammonium. Ammonium is one of the there's only 2 of these, 2 polyatomic cations. Okay, so down here we have ammonium, so NH4 with a +1 charge. So NH4 with a +1 charge. And then we have bromide. Bromide is just bromine, and bromine has a -1 charge. So these we just put together. So NH4 and then Br. We do not need parentheses on our ammonium because there's just one of them. So we just write it just like that. All right, aluminum, Al, has a charge of +3. Fluoride, IDE, is just fluorine. Fluorine has a -1 charge. So since aluminum's +3, fluorine's -1, I need 3 fluorines to make this work. So it's going to be Al, F, and then we need 3 of those. So we'll add a 3 onto the end. All All right, manganese is Mn. This right here, this 4, means that we have a +4 charge. And then sulfur is sulfide, so this will be S, and sulfur has a charge of -2. So to make this work, I'm going to need 2 sulfurs, so it'll be MnS2. All right, iron is Fe. And again, we have Roman numerals, so that means we have a +3 charge. Okay, now phosphite. Phosphite is not phosphorus, it ends in ITE. So phosphite, we're going to have to go to our table here and go up here. So phosphite is right here. It's PO3 with a -3 charge. So PO3 with a -3 charge. Since iron and phosphite are both magnitude 3, so one's positive, one's minus, I just push them together. So it'll be Fe PO3. All right, moving on. We have hydrofluoric acid. Okay, so hydro means that we do not have an oxygen. We're just going to have hydrogen. Hydrogen is always just a +1. And then fluoric is fluorine. Fluorine on the periodic table is a -1 charge. So we just push these together. It's just going to be HF. Okay, phosphorus acid. Okay, now this one's a little tricky. So it's phosphorus acid. So we know it's not phosphorus, even though it just says phosphorus acid. Because we don't have hydro, that means it's going to have an oxygen. So let's go and look on our polyatomic table here. Okay, so we have phosphate and phosphite. Okay, since it's phosphorus acid, the only one that's going to work here, remember we change our endings, since it ends in ITE, we're going to change the ending to OUS. Okay, so it's going to be phosphite, which is PO3. Okay, so there's no hydro. We know there has to be an oxygen, so the only one that'll work is going to be phosphite. So we're going to have hydrogen, and we're going to have phosphite, which is PO3. Remember, this has a -3 charge, so I need 3 hydrogens to make that work. Okay, so let me just kind of write this off to the side. PO3 and a -3 charge, so we needed 3 hydrogens to make that work. Okay, sulfuric acid, again, no hydro, so we know that there has to be an oxygen. It can't be sulfur because there isn't a hydro. So let's go look at our table here. Okay, so we have sulfate and we have sulfite. Since it's sulfuric acid, okay, it has to end in ATE. Okay, so let's go back here. So the only one that'll work is SO4, okay, which has a charge of -2. Hydrogen, remember, has a charge of +1, so I'm going to need 2 hydrogens to balance this out. All right, acetic acid. No hydro, so there has to be an oxygen. So let's go take a look at our table. And, right up here, acetate. Okay, so it was acetic acid. So the whole TATE is going to get taken off here. All right, and we're going to end up with acetic acid. So let's go back here. So let me write that out. So it's going to be CH3. Whoops. Let's go back and let's redo that. So it was CH3, CO2. And that had a charge of -1. That whole thing, -1. So we're just going to smash that together with our hydrogen. Don't worry about combining like terms here. Just write it out exactly like you see it. And that's it. Okay, lithium carbonate. Lithium is Li. Lithium is Li with a +1 charge. Carbonate is not carbon. We have to go to our table here. Okay, so carbonate is right here, CO3 with the -2 charge. Since it's a -2 and lithium's a +1, I'm going to need 2 lithiums. So it'll be Li2CO3. So that's lithium carbonate. All right, number 3 says, there are 3 transition metals that do not get a Roman numeral. Identify them and their respective charges. Okay, so there are 3 of them. The first one is silver. Okay, silver Ag will always be a +1. We have zinc. This is one that we did recently. We used this one recently in our lab. This one's going to be a +2 charge. And then finally we have cadmium. Okay, that's Cd, and it has a charge of +2. All right, number 4 says, examine the following names and formulas for errors. Identify each as correct or incorrect. If incorrect, explain the error and correct it. So we have cobalt nitride. Cobalt nitride. Okay, so let's just take a quick peek and see where cobalt is on our periodic table. So cobalt is in the middle. Cobalt is in the transition metal area, so it's going to have a variable charge. So there should be a Roman numeral there. Okay, and then nitride is going to be on our table here. Oh wait, no it isn't. Nitride is nitrogen. Come on, what are you doing? Nitride is nitrogen. Okay, so for this one, to make it work, cobalt is a transition metal. So cobalt has multiple oxidation states. And needs a Roman numeral in the name. Okay, SrCl2. Okay, so let's look at the ions here. So we have strontium. Strontium on the periodic table has a charge of +2. And then chlorine, Cl, has a charge of -1. So all ionic formulas, all ionic compounds are neutral. So they shouldn't have a charge. If I had 2 strontiums, that would be a total of +4. If I had 2 chlorines, that would be a charge of -2. So I would end up with a charge, an overall charge of -2. So this should be we need strontium, which is a +2, and then we need 2 chlorines, and that would be 0. So 2 chlorines gives us an overall negative of -2, strontium +2, put them together, and 0. All right, same thing on the next one. We have hydrogen. Hydrogen is +1. Let's look at the charges here and make sure we're good. PO3, phosphate, PO3, has a charge of -3. So if I just put them together like they did, I'd have an overall charge of -2. So this one should be I need 3 hydrogens to make this work. So H3, PO3. All right, calcium 2 phosphate. Okay, well, let's just double check because I don't think calcium is in the transition metals, is it? No, calcium's right here. So calcium doesn't change its charge. It's always going to be a +2 charge. So here, calcium doesn't have multiple oxidation states. Okay, so we are done with the first page. Let's move on. Okay, number 5 says, explain the difference between ionic bond formation versus metallic bond formation. Be specific about how two electrons contribute to the bonds. Be specific about how electrons contribute to the bonds. Okay, so in ionic bonds, the electrons get transferred. So we go from cation to anion. So electrons transferred. So we go cation to anion. Okay, next we have metallic bonds. And with metallic bonds, remember what happens? We have a sea of delocalized electrons. Okay, so metallic bonds are held together just by sharing electrons. So electrons are shared in a sea of delocalized electrons. All right, identify the charge of the cation and the anion in the compound 3, 2. All right, so this happens quite often where we end up with something like this, where we have to have kind of a weird thing going on here. So I know for sure the cation is going to be +2, and the anion will be -3. And here's how I know that. So we have 3 of the cations. Okay, so +2 times 3 gives us +6. The anion, we have 2 of them, so -3 times 2 equals -6. Okay, and then when we add those up, we end up with 0. You can try any other number combination, but that's going to work. So when we work through ions, what will often happen is we'll end up with a situation where one of them is +2 and the other one is +3. So you end up having to find a least common multiple here for it to work. So the multiples of 2 are 2, 4, 6, 8. The multiples of 3 are 3, 6, 9, 12. So a common one that comes up here is when you have to get them to equal 6. So you should hopefully be familiar with this one because it's come up quite a bit. Okay, number 7 says, identify the ratio of elements when lithium combines with selenium. So lithium, Li, has a charge of +1. Selenium, Se, on the periodic table is -2. So I need 2 lithiums for every selenium. So it's going to be 2-to-1 ratio, which means that we're going to end up with Li to Se. Write the electron configuration of the carbon anion. Identify the noble gas and 2 additional ions that are isoelectric to the carbon anion. All right, so let's go look at our periodic table. So carbon is right here, and carbon is on the second row, and it's in the P block. It has 6 total electrons. So carbon by itself Okay, so again, 6 electrons, it's going to be 1s2, 2s2, 2p2. Okay, so that's normal carbon. Now, if it's asking for the carbon anion, that means it's going to have a negative charge. When carbon ionizes, it needs 1, 2, 3, 4 electrons to get to the noble gas. So it's going to be C minus 4. So instead of having 6 electrons, it's going to have 10. So let's just add on 4 more electrons to this. 2s2 and then 2p. Remember, the p block will hold up to 6, so 2 plus 4 gives us 6. All right, so isoelectric means you have the same number of electrons or the same electron configuration. So if we go to our periodic table, neon has the same number of electrons. So noble gas would be neon. And what are some other ions that are isoelectric to carbon? The carbon ion. So fluorine. Fluorine has 9 electrons. Fluorine with a -1 charge would have 10. So it's isoelectric. What about, let's go to the other side. Let's do sodium. Sodium has 11. So to write sodium with 10, sodium would be +1. So it has 1 less electron. So instead of 11, it has 10. Okay. 9 says platinum has 2 possible cations, +4 and +2. Write the formula and name each possible ionic compound that platinum can form with oxygen. So, a lot of big words here, but don't panic. So platinum is Pt, and it's either going to be +4 or +2. So platinum with a +4 charge and oxygen, which is -2. To make this work, I'd need 2 oxygens. So my formula would be PtO2. And remember, since platinum has multiple states, we're going to use Roman numerals. This will be platinum. And it has a charge of 4, so it'll be platinum 4. And then oxygen, we change the ending, oxide. Okay, if platinum has a +2 charge, oxygen has a -2 charge, we just smash them together. So platinum and oxygen. Since platinum has a +2 charge, this will be platinum 2 oxide. Okay, 10 says, sketch the Lewis dot diagram for the ionic bonding of potassium and sulfur. Okay, so we've got potassium, which is K. Potassium has 1 valence electron, so it gets 1 dot. And then sulfur. Sulfur has 6 valence electrons, so it gets 6 dots. All right. Sulfur wants electrons. It has 6, it needs 2 more to get to 8. Potassium wants to give up its electrons. It has 1, and below that, it has a full outer shell. So potassium is going to give up its electron to sulfur. So now sulfur has 7, still needs 1 more. So let's throw another potassium in here and transfer that. So both potassiums gave up their valence electron. Sulfur picked up 2 more. So now sulfur's happy, it has 8. So to write out our ions, we have potassium. Potassium gained an electron, so it'll have a charge of +1. Sorry, let me re-say that. Potassium lost an electron, so it'll have a charge of +1. Sulfur gained 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So it'll have a charge of -2, and then we had 1 more potassium. So just a note on here, if you lose electrons, you're going to have no dots. If you gain electrons, like sulfur, you want to show all 8 dots. Okay, write the formula and the name of the ionic compound. Remember, the cation goes first. So cation is potassium. There are 2 of them, so K2, and then S for sulfur. Our name is going to be potassium. And then it's sulfur. We change the ending, so it's going to be sulfide. Explain how this bonding impacts the stability of each element. Okay, so potassium losing electron exposes a full outer shell. Full outer shell below. Okay, and then you have sulfur. Sulfur gaining electrons. Fills outer shell completely. So here's what I mean. So potassium, so you've got an atom, all right, and this isn't necessarily potassium, but let's say you had an atom, so this is actually going to be lithium. So I've got an outer shell here, and then this shell right here only has 2 electrons. That's the full outer shell on the first level. So if I get rid of this 1 electron, I have a full shell right here. Okay, so it's like peeling an onion almost. All right. And sulfur had 6. It only needs 2 more, so if I gain 2 more, now I have a full outer shell. Going here. So number 11, use the Bohr models below to answer the following questions. Write the formula and the name of the ionic compound that will be formed by the atoms. Draw the Lewis dot diagram for each atom, and then use Lewis dot diagrams to show the formation of the ionic bond. All right, so got a Lewis diagram here. Okay, so we have 15 protons. 15 protons. If we look that up, that's phosphorus. Okay, this one here has 19 protons. 19 protons is going to be potassium, K. All right, so write the formula and the name of the ionic compound that will be formed. So we have potassium, K, that's going to be our cation. It's a +1 charge. Phosphorus, P, is a -3 charge. So we'll need 3 potassiums. So this will be K, 3, P, and it's going to be potassium. Okay, this is phosphorus, so we'll change the ending to phosphide. Draw the Lewis dot diagram for each atom. So we have potassium and we have phosphorus. Phosphorus has 5 valence electrons. 1, 2, 3, 4, 5. Use Lewis dot diagrams to show the formation of the ionic bond. Okay, so we have phosphorus. We have potassium. Potassium will transfer to phosphorus. Phosphorus still needs 2 more, so let's throw in 2 more potassiums. Looks like that. So we'll have 3 potassiums. Each potassium is going to have a +1 charge because they're giving up 1 valence electron. And then we have phosphorus. Phosphorus gained 3 electrons for a total of 8. Its charge will be -3. All right, number 12 says, list the 7 diatomic elements. Okay, so the saying that I have is, I have no bright or clever friends. So iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, fluorine. So hydrogen, nitrogen, bromine, oxygen, chlorine, fluorine. Okay. Diatomic elements are elements that can't be by themselves. So they're either going to be paired up with something or there's going to be 2 of them. So like oxygen, for example. Okay, so oxygen, for example, you'll never see it just written as O. It'll be written as O2. Okay, it's diatomic. Balance the following reactions and identify the reactions as single displacement, double displacement, or acid-base. Okay, so don't let this confuse you right here for the first one. So we have chlorine, which is a -1 charge. We have potassium, which is a +1 charge. And then we have bromine, which is a -1 charge. So even though there's 2 chlorines, don't get confused and think it might be a double replacement. It's still only 1 ion. So chlorine will pair up with potassium, which is what you see on the right side. And then we have bromine. So chlorine and bromine are both diatomic. So they can't be by themselves, so that's why there's a 2 there. Okay, let's balance this. So if we go to balance this, we're going to make our table here. So we have chlorine, potassium, bromine, chlorine, potassium, bromine. Okay, so if we count these up, I see 2 chlorines, 1 potassium, 1 bromine. On the product side, I see 1 chlorine, 1 potassium, 2 bromines. So my chlorines aren't balanced on the right side, so I can put a 2 here. Remember that 2 goes to the potassium and the chlorine. So 2 times 1 makes this 2. 2 times 1 makes this 2. So chlorines are good, but now the potassiums and the bromines aren't on the left side. So let's put a 2 here. So again, this distributes to both terms. 2 times 1 makes this 2. 2 times 1 makes that 2. Okay, so we are balanced. I'm just going to go ahead and throw 1s in here. I like to leave anything blank. Okay, so this is a single displacement reaction. Okay, so single replacement will always be one thing by itself, which was the chlorine in this case, and then you had a compound, which was the potassium bromide. So the chlorine switched out with the bromine. That was a single replacement. All right, this next one, we have 2 compounds. We have barium fluoride, and then we have potassium phosphate. So this is going to be a double replacement. So the cations are going to switch places. And we end up with 2 brand new compounds. So let's balance this one. So we have barium, fluorine, potassium, and then PO4. Do the same thing on both sides. Okay, so barium we have 1, fluorine we have 2, potassium 3. So I'll have one of those. Barium 3, 2, 1, 1. All right, so this one's kind of a doozy. So let's start with the bariums. We have 3 on the right, we have 1 on the left. So let's put a 3 here and see what happens. 3 times the 1 barium makes this a 3. 3 times the 2 fluorines makes this a 6. Okay, so barium's good. Fluorine, we have 6 on the left, 1 on the right. So let's put a 6 here and see what happens. So we have 6 times 1 makes this 6. 6 times 1 makes this a 6. Okay, so the fluorines are balanced now. Potassium, we have 6 on the right, 3 on the left. So let's put a 2 here. 2 times 3 makes this 6. 2 times 1 makes this 2. I'll just put a 1 there. Great, all balanced. Okay, complete the following reactions. Okay, so we got to do a little bit more work here. We have to figure out what goes where. So we have hydrogen, we have sulfate, SO4, we have magnesium, and we have hydroxide. Hydrogen's +1, sulfate is -2, magnesium +2, and hydroxide -1. This is a double replacement reaction, okay? But if you look closely here, we have hydrogen and we have hydroxide. Okay, so this is actually a special kind of a double replacement. This is an acid base. Okay, so hydrogen will pair up with the OH, so this will be H2O. And then we have magnesium and sulfate. Sulfate's -2, magnesium's +2, so this will just be magnesium, sulfate, MgSO4. Okay, to balance this, we've got hydrogen, sulfate, magnesium, and hydroxide. Whoops, scratch that. We're going to break up hydroxide, so we'll just need an O there. Okay, and then on the other side, we have hydrogen, sulfate, magnesium, and oxygen. So let's count them up. So we have 2 here, and then we have another 2. So this will be 4 hydrogens. We have 1 of those, we have 1 of those, and then 2 oxygens. Okay, again, this 2 on the outside multiplies in. Okay, on the other side, we have 2 hydrogens, 1 sulfate, 1 magnesium, 1 oxygen. Okay, so this one's pretty easy to balance. All I need to do is just put a 2 in front of H2O. 2 times 2 is 4. 2 times 1 is 2. Okay, and that one's balanced. All right, so I have aluminum by itself, and then I have a compound here. Okay, so this is going to be a single replacement. So we have aluminum. Aluminum's +3. We have hydrogen, which is a +1. And then we have PO3, which is a -3. So aluminum will match up with that. So both of those are 3, so this is going to be AlPO3, and then you're going to have hydrogen. Now remember, I have no bright or clever friends, so this hydrogen can't be by itself. There's going to be 2 of them. All right, and now we balance. So 1, 3, 1. Don't let that 3 confuse you. It's part of the ion. Okay, so it's still just 1. On the other side, we have 1, 2, 1. Okay, so aluminums are balanced, hydrogens are not, but this is that unique situation where we have a 3 and a 2. I can't multiply the 3 and have it turn into 2. I can't multiply 2 and have it turn into 3. So we're going to have a least common multiple. The multiples of 2 are 2, 4, 6, 8. The multiples of 3 are 3, 6, 9, 12. So I can multiply 2 and have it turn into 6. I can multiply 3 and have it turn into 6. That's our least common multiple. So to make this work, what we're going to do is we're going to multiply our hydrogen on the left by 2. So 2 times 3 makes this a 6. 2 times 1 makes this a 2. On the other side, 3 times 2 makes it 6. So 2 times 3 is 6. So our hydrogens are balanced now. Okay, but our PO3s, not so much. So I need 2 on the right to balance with the 2 on the left. So let's put a 2 here. 2 times 1 is 2. 2 times 1 is 2. And then just to finish this off, we need a 2 here. 2 times 1 is 2. Okay, and we are balanced. Okay, 15. Chlorine is mixed with lithium sulfide. Write the complete molecular equation for this reaction. So we have chlorine, which is -1. We have lithium, Li, which is +3. And then we have sulfide, which is sulfur, which is a -2. This is going to be a single replacement reaction. Chlorine and lithium will pair up. So let's write out the left side. So we have Cl. I have no bright or clever friends, so chlorine will need to be paired up here. Okay, and then we have lithium. Lithium is 3, sulfur is 2. Okay. Ooh, I made a goof here. Lithium is not 3. Lithium is actually 2. Okay. No, I made another goof. I made a double goof. Lithium is just a +1. Okay. All right. So we're going to end up being lithium, 2, and then sulfur. So lithium sulfide. Okay, and then on the other side we have, as we figured out earlier, lithium and chlorine are going to go together, so it'll be LiCl, lithium chloride. Okay, and then we have sulfur. I have no bright or clever friends. Sulfur's not on that list, so we're good. And then let's balance. Chlorine, lithium, sulfur. So 2 chlorines, 2 lithiums, 1 sulfur, 1, 1, 1. This is a really easy fix. We just need to put a 2 right here. 2 times 1 makes this 2. 2 times 1 makes that 2. Okay, balanced. This is a single replacement reaction. Okay, now it says name the 2 products of the reaction according to the naming rules. Okay, so LiCl, we already did this. This is lithium. So we never change the cation, and chloride. So it's chlorine, but we change the ending to IDE. Okay, and then S is just sulfur. All right. Silver nitrate reacts with potassium chromate to yield silver chromate and potassium nitrate. Write the complete molecular equation. Predict states of matter according to the solubility rules. All right, so silver nitrate. So we have silver, Ag. Nitrate is NO3. And then we have potassium. Oh, yeah, potassium. Potassium. And chromate, CrO4. Okay, so silver, we have to look at what it's attached to for a charge. Nitrate is -1, so silver is going to be a +1. Potassium is +1, and then chromate is -2. So this will be a double replacement reaction. So let's start with writing out the left side. So we have silver nitrate, so AgNO3. Then we're going to have potassium chromate. We need 2 potassiums to make this work, CrO4. And then that's going to yield, so double replacement reaction, we're going to have potassium nitrate. Okay, and then we're going to have silver Ag. We need 2 of those. Okay, we need 2 of those because silver is a +1 and chromate is a -2, and then CrO4. Okay, so let's go through, and I think I can split screen this. Let's go through and let's take a look at the solubility rules. So on the very last page, we have our solubility rules. So AgNO3. So here's how this works. Okay, so we find Ag, which is, whoops. We have Ag, which is here. We have NO3, which is here, and we just find where they match up. Okay, so it says soluble. If it's soluble, it's going to be aqueous, AQ. Okay, the next we have potassium, which is K, and then chromate, which is CrO4. So we follow that down. It says soluble, so it's going to be aqueous. Don't get confused. The SOL doesn't mean solid, it means aqueous, which means it's dissolved in water. It's soluble. Okay, potassium, K, and then NO3. So just follow that down. It says soluble, so that's going to be aqueous. And then we have silver, which is Ag, and then chromate, CrO4. Okay, so this one says insoluble. If it's insoluble, it's going to be solid. All right, so those are the states. The only other thing we have to do here is make sure that it's balanced. Okay, so let's go ahead and balance. So we have silver, Ag, NO3, potassium, and then chromate, CrO4. On the other side, same thing. Okay, so 1, 1, 2, 1, 2, 1, 1, 1. All right, so let's start with the potassiums. Okay, so potassium, let's put a 2 here to balance that out. So 2 times 1 is 2, 2 times 1 is 2. And then our potassiums are good. Silver and nitrates, not so much, so let's put a 2 here. 2 times 1 is 2, 2 times 1 is 2, and we are balanced. So much fun. Okay, let's go down to 17 here. Solid magnesium metal reacts with sulfuric acid to yield magnesium sulfate and hydrogen gas. Write the complete molecular equation, predict states of matter according to the solubility rules. Okay, so it tells us in the question, solid magnesium metal. Okay, so that's going to be MgS. Okay, we have magnesium. Magnesium is +2. Sulfuric acid. So that's H2SO4. How did I know that? Well, let's see. You've got hydrogen, which is a +1, and then you have sulfate, which is a -2. I need 2 hydrogens to make that work. Acids are always aqueous. Okay, so this is a single replacement reaction. So magnesium will go with sulfate. So MgSO4. And then it says hydrogen gas. Okay, so that one's kind of easy. So we'll just have hydrogen. I have no bright or clever friends. Hydrogen is diatomic. You're going to need 2 of those. And it tells you it's a gas. So let's just throw the G right there. The only one we have to look up is magnesium sulfate. So magnesium is right here. Sulfate, SO4. It says soluble. So this is going to be aqueous. And let's balance. Magnesium, hydrogen, sulfate. Okay, so 1, 2, 1, 1, 2, 1. Oh, look at that. The stars have aligned. It's already balanced. All right. Lead 2 nitrate reacts with sodium sulfate. Predict the products to write the complete molecular equation. Predict states of matter according to the solubility rules. All right, so we have lead, Pb, lead 2, so +2. Lead 2 nitrate, nitrate is NO3 with a -1 charge. Sodium sulfate, so sodium is Na, its charge is +1. And sulfate is not sulfur, it's SO4 with a -2 charge. Okay, so we have Pb, lead is +2, nitrate, NO3 is -1, so I'm going to need 2 nitrates, so throw up parentheses. Okay, and then we have sodium sulfate, so Na, kind of the same thing. Sodium's +1, sulfate -2, so I need 2 sodiums. Okay, double replacement. So we'll have lead, Pb, sulfate. Then we have sodium and NO3. All right, let's split screen this again, and let's go through and figure out our charges. I meant states. So we have PbNO3. So lead is PbNO3. Let's just kind of go down here. It says, let's see, Pb and then NO3 is soluble. Okay, so that's aqueous. Sodium sulfate. Okay, so Na and then sulfate, SO4, says soluble, so aqueous. PbSO4, so lead, and then sulfate, oh, insoluble, so solid. And then NaNO3, so sodium, and then NO3, oh, they're all soluble, so aqueous. Okay, so those are our states. Let's balance this. So we have lead, nitrate, sodium, and sulfate. Okay, so lead, 1. Nitrate, we have 2. Sodium, 2. Sulfate, 1. 1, 1, 1, 1. Okay, let's see here. So, oh, this one's easy. Let's just throw a 2 right here. 2 times 1 is 2. 2 times 1 is 2. Oh, it's balanced. Okay, 19 says, write the total ionic equation for question 18. Okay, so when we do an ionic equation, anything that is aqueous, so it has the AQ in parentheses, we split it apart into its ions. So let's start with the first one. So we have lead, Pb. Lead is a +2 charge, and it's aqueous. We have, okay, now if you have a 2 out here, we bring that 2 to the front for the net ionic. So 2NO3 minus 1. Okay, again, we have a 2 here, so we're going to bring that out front. Okay, so it's 2Na plus 1. Okay, and I'm forgetting to write the states here. Whatever state it is when it's in a compound, that state carries over. Okay, so don't worry about looking at each individual piece. So whatever it is here is what it's going to be down here, okay, when it's attached. Okay, so let's see. Where do we leave off? Sulfate, SO4. So don't get confused and try to pull this 4 out. The 4 is part of the sulfate, so it's just going to be SO4 with a -2 charge. All right, on the other side, we have lead and SO4, but it's a solid. We do not split up solids, so this will just be PbSO4, solid. Okay, and then this 2 distributes to both terms. So it'll be 2Na plus 1 plus 2NO3. NO3 is -1, and I'm forgetting again to put the states here. Okay, anything that exists on both sides, well, let's switch up and do a different color here. Anything that exists on both sides, we can cross off. So this exists on both sides. Let's cross that off. What else do we see on both sides? I see sodium on both sides. And I believe that is it. Okay, so let's go back here, and this should be aqueous. Terrible here. All right, our net ionic equation is anything we didn't cross off. So we have lead, Pb, +2, aqueous. We have sulfate, SO4, -2, aqueous. That goes to Pb, SO4, solid. Spectator ions are anything we crossed off. You do not need the numbers, you do not need the states. Okay, so this will be NO3. When I say numbers, I meant the coefficients. Okay, we still need our charges. And then we have Na plus 1. Ta-da! Okay, 22, it says, magnesium nitrate reacts with potassium hydroxide, predict the products, yada, 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 predict the states of matter. All right, so excited. All right, so we got magnesium, Mg, nitrate, which is NO3. Magnesium is +2, nitrate -1. Potassium hydroxide, K plus 1, hydroxide, OH, minus 1. This will be a double replacement. Okay, so magnesium nitrate, Mg, and then NO3. Magnesium plus 2, nitrate minus 1, so I need 2 of these. And then potassium hydroxide, so KOH. That goes 2. So we're going to end up with magnesium hydroxide. Magnesium is plus 2, hydroxide minus 1, so MgOH is going to go in parentheses, the 2. And then we have potassium nitrate, KNO3. All right, let's look at our states. So MgNO3, so magnesium, and then NO3 is soluble, so this will be aqueous. Potassium, K, and OH, these are all soluble, so this will be aqueous. Magnesium and hydroxide, so magnesium and, insoluble. Solid, and then potassium, K, and O3, these are all soluble, so this will be aqueous. Okay, now we balance. So magnesium, nitrate, potassium, and hydroxide. One, two, 1, 1, 1, 2, 1, 1. All right, so let's see, we need to balance our hydroxide. So let's put a 2 here. 2 times 1 makes this 2. 2 times 1 makes this 2. Okay, so I balanced out the hydroxides, potassium, and nitrate, not so much. So let's see, if I put a 2 here, 2 times 1 is 2, 2 times 1 is 2. Balanced. Okay, write the total ionic equation. So again, split up anything that is aqueous. So we have Mg plus 2, aqueous. We have 2 NO3 minus 1, aqueous. This 2 goes to both. So there's going to be 2 potassiums with a plus 1 charge, aqueous, plus 2 OH minus 1, aqueous. On the other side, this is a solid, we leave it alone. Okay, and then again, this 2 distributes to both terms. So 2 potassium, and then 2 NO3 aqueous. NO3 is minus 1. Oof, almost ran out of space there. Okay, cross out anything that exists on both sides. So I see this, NO3 on both sides. I see potassium on both sides. And I believe that's it. So the net ionic equation is anything left over. So we've got magnesium plus 2 aqueous. We've got 2 OH minus 1 aqueous. That goes to Mg OH 2 solid. Okay, identify spectator ions. So that's anything we crossed off. So if we go back up, it was our nitrate and our potassium. Okay, we don't need the coefficients and we do not need the states. So this will just be NO3 minus 1 and potassium plus 1. Okay, this is our last one here. So it says barium nitrate solution is mixed with sodium sulfate solution. Identify this reaction as single displacement or double displacement. Okay, displacement and replacement are interchangeable here, and then how do you know? Okay, so we have barium Ba, nitrate, which is NO3. We have sodium sulfate, Na, and then SO4. Okay, let's throw some charges up here. Plus 2, minus 1, plus 1, and minus 2. So This will be a double displacement or double replacement. Same thing. Okay, how do we know? Well, there are two ionic compounds. It's two things that are combined. So two ions that are combined, and we have two compounds. So two ionic compounds. Write the complete molecular equation for this reaction. So we've got barium and nitrate, NO3. Barium's +2, so I'm going to need 2 of these nitrates because they're -1. We have sodium sulfate. Sodium's +1, sulfate -2, so I'm going to need 2 sodiums. Okay, on the other side, barium and sulfate are both magnitude 2, so it'll be BaSO4. And then we have sodium, NaNO3. Okay, let's look at the states here. So BaNO3 is soluble, so this will be aqueous. Na2, SO4, so Na is soluble, aqueous. Barium sulfate, Ba, sulfate, SO4, insoluble, so this will be a solid. And then NaNO3. They're all soluble, so this will be aqueous. Okay. So let's balance this. So we have barium, nitrate, sodium, sulfate. Okay, so 1, 2, 2, 1, 1, 1, 1, 1. All right, this one's an easy fix. I'm just going to throw a 2 here. That makes this a 2. That makes that a 2. Write the total ionic equation for this reaction. So anything that's aqueous, we split up. So we have barium, Ba, +2, aqueous. We have 2 NO3. NO3 is -1, aqueous. We have 2 sodiums, so 2 Na +1, aqueous. We have SO4 sulfate, SO4 -2, aqueous. This next piece on the other side is solid, so we leave it alone. BaSO4, solid. And then we have one more. This has a 2 in front. That 2 goes to both terms. 2 Na +1, aqueous. And then 2 NO3, aqueous. NO3 is -1. Okay, so let's see what we can cross off on both sides. So barium, nope. This NO3, yep, it exists on both sides. We can cross it off. Sodium Na is on both sides. Let's cross that off. And I think that's it. Write the net ionic equation for this reaction. Anything we didn't cross off. So Ba +2, aqueous. We have sulfate, SO4, -2, aqueous. That goes to barium sulfate, solid. Okay, identify the spectator ions, anything we crossed off. So NO3, -1, and sodium, +1. All right. Name the two products of this reaction according to our naming rules. Okay, so the two products, we don't have 2 products, we only have 1 product. That's interesting. So, oh, wait a minute, I got it. 2 products according to this reaction. It's not talking about the net ionic reaction. Okay, so the other 2 products we're gonna have, if we go back up here, it's talking about the molecular. So BaSO4 and then NaNO3. So NaNO3, sodium, Na, so sodium, and then NO3 is nitrate. We don't change the ending because NO3 is polyatomic. The other one we had was BaSO4. So that's barium, Ba. And then SO4 is sulfate. Is that the last question? Wow. I don't know about you, but the last hour and 10 minutes has been the most fun of my entire life. I hope it was the same for you. So that was the study guide. You got this test. Good luck.